Good morning, everyone, and welcome to our team capstone presentation, A Head Start on Early Childhood Education. We'll start with introductions to our team. I'm Elijah Blackwell. I have a background in community planning and digital media, and I'm passionate about the intersection of design and data to support organizational storytelling and design more equitable systems.
I'm Kathleen Matos, and I have a background in web development, and I took this bootcamp to further expand my skill set.
Hello, I'm Gabriel Fossey. I have a background with Linux systems and penetration testing. I took this bootcamp to bolster my knowledge of Python and harness the power of machine learning applications.
We'll share an overview of our process, starting with an introduction to Head Start, our problem definition, how we engage domain experts, the insights we gained into early childhood in New Mexico. We'll provide an overview of our data collection process, our analysis methods, visualizations, and we'll wrap up with conclusions and next steps before opening up to questions. So Head Start and Early Head Start are federally funded early childhood education programs that provide wraparound support services to families with incomes at or below the federal poverty line. Early Head Start serves prenatal to age 3, and Head Start serves children ages 3 to 5. Our project implements unsupervised learning methods to identify underserved communities in New Mexico eligible for Head Start centers. By analyzing Census Tract demographics, we'll apply hierarchical clustering to group tracts with similar socioeconomic indicators. Underserved communities will be identified by reviewing the distribution of Head Start centers within clusters. We engaged domain experts across 5 key organizations. We met with policy advocates at the University of New Mexico's Cradle to Career Policy Institute. It's great to have Dana and Ruth join us from the Policy Institute today. The New Mexico State University's Anna Age 8 Institute, the New Mexico Early Childhood Development Department Partnership, and our Early Learning Advisory Council members, as well as Office of Head Start officials. Domain experts gave insights into early childhood in New Mexico. We learned that 27% of children live in poverty, 36% of parents lack secure employment, 17% of families experience food insecurity, and each of these factors contribute to children in New Mexico having some of the highest exposure rates in the nation to adverse childhood experiences. We collected data across 5 key sources to identify gaps in the continuum of care for youth. The 2017 New Mexico Census provided insights into demographic information, including gender, race, ethnicity, age, income, and employment. The 2018 New Mexico Education Tracts dataset includes educational attainment information and current population enrolled in school for each census tract. The 2019 University of New Mexico's Cradle to Career Policy Institute's Early Childhood Education Map Visualization provided data on preschool enrollment and Head Start center location data. The 2019 New Mexico Early Childhood Development Partnership provided a comprehensive needs assessment of the Head Start programs, and the Office of Head Start provided enrollment statistics information. Gabriel will introduce key concepts to our data analysis methods.
All right, these are some of the tools we used for our project and throughout the bootcamp. In particular, our capstone has relied on Google Colab, Python, XGBoost, scikit-learn, pandas, GeoPandas, and matplotlib. We merged many kinds of data like GeoJSON, polygons, education, and census data. However, much of the data from the government was inaccessible, and there was a lack of centralized sources for early childhood data. Although we got a lot of useful information from the Head Start organization itself, we found that we had to look outside Head Start to find much of the data that we were looking for. With some difficulty, we were able to merge disparate sets of data by using their census tract IDs. It allowed us to combine educational, geographic, economic, and demographic information into one data frame. This provided much more robust resource to address our problem definition. We also collected the locations of all the known Head Start centers throughout New Mexico. We dropped null values when applicable, for instance, locations that didn't have coordinates or displayed 0 funded slots. Finally, we were able to take the Head Start locations and create a distance map to help us identify communities that were most in need, in accordance with the clusters we created through data processing. To start, we need to know what a census tract is. Census tracts are geographic borders created by the Bureau of Census for analyzing the population. Population varies from about 1,000 to about 10,000 people per tract, with an average of 4,000. And the size can vary from about the size of a neighborhood to nearly the size of a country, depending on population density. New Mexico has about 500 tracts in all. With a vast amount of features, we narrowed our selection to those that were deemed most useful for our problem definition. These are economic data, such as income and poverty, racial and ethnic demographics data, and education, such as enrollment and educational attainment data. To process our data, we looked at a few different things. Throughout this boot camp, we've used a lot of the most popular machine learning models. We have looked at supervised models such as naive Bayes, decision trees, linear regression, random forests, and XGBoost. We also worked with some unsupervised models, including k-means clustering, hierarchical clustering, and principal component analysis. For our project, we chose to focus on linear regression, XGBoost, k-means clustering, and hierarchical clustering. Linear regression models explore the linear relationship between targeted outcomes and one or more of the features of our data. XGBoost is a clever variation of decision tree that penalizes features that don't help with prediction. K-means clustering uses top-down divisive clustering and tends to cluster the mean variance of observations. Hierarchical clustering makes a hierarchy of clusters and uses an agglomerative method to merge smaller clusters into larger ones. So we looked at some supervised models first. For XGBoost, the prediction target was Head Start funded slots for kids in each census tract. But this model is not ideal for this data because of the lack of a real trend that we will see in the next slide. However, XGBoost provides useful insight into which features are most important for data for prediction, namely income and child poverty. Then we used an ordinary least squares regression. Linear regression explores the relationship between the target Head Start funded slots and the features of our data frame. There isn't a clear trend as we can see in the plot, where the actual values for the funded slots are seen on the x-axis and the predicted values are on the y-axis. A perfect trend would be seen along this diagonal line. Then we applied k-means clustering. K-means tries to divide the data into evenly sized clusters. The error only goes down when you reach a high number of clusters, which would not provide a discrete way to describe the communities that our clusters are comprised of. Finally, we applied hierarchical clustering. This dendrogram on the left shows how different thresholds can output different amounts of clusters. The longer the line on the y-axis conveys greater variance between those clusters. We chose to set the threshold at 6 clusters to have a significant amount of neighborhoods grouped together by similar socioeconomic indicators. The clustering plot shows the variance in cluster grouping that k-means couldn't capture. For example, 1, 5, and 4 are really tight clusters, whereas 3, 2, and 0 are more spread out. In this plot, we see how clusters are ordered on a two-dimensional grid, which is easier to interpret when looking at multi-dimensional data.
All right, so let's take a look at the clusters that we've created using our processing. And from our analysis, we have made a couple of conclusions about these clusters. Cluster 1 is overall the most in need, but also the most well-served. This may be in part to having a high Native population and access to the tribal Head Start program, which is not available to some of these other communities. Cluster 6 is the largest with 213 tracts and generally needs the least help. Clusters 4 and 5 have the second and third highest number of Head Start funded slots per 1,000 residents and are both in the lower half of our group for levels of child poverty, which leaves us clusters 2 and 3, which have the second and third highest levels of child poverty, but have 2 of the lowest numbers of Head Start slots. So we're going to be focusing on these clusters moving forward. So we decided to create an interactive map to better visualize our data and gain some more insight into our clusters and the way that they're laid out. We decided on the Python library Folium to build our map and used another package called Shapely to determine in which tracts the current Head Starts are located. All right, let me jump over to our map real quick. All right. So you can see here, each cluster is represented as a different color, and all of these pins represent Head Start and early Head Start centers. So I'm going to turn these off for just a moment. And you can see some trends popping up right away with this block of yellow up here in the top left, which is cluster 1 with the high Native population. And the majority of the state is this pinky color, which is cluster 6. Cluster 2 here is green and cluster 3 is blue. When you zoom in, you can see that the more densely populated areas result in much smaller clusters. And so one important little tooltip that we added here in this, when you hover over a census tract, it gives you some information about that tract, including race and ethnicity information, income and poverty levels, and some basic info, such as the county that it's located in and the population. And another thing we added was a stat that we called nearest Head Start in miles, which is the distance from the center of a census tract to the nearest Head Start location. So I'm going to turn the Head Start locations back on. And so one tract I want to point out is this one down here, where the distance from the center of the tract to the nearest Head Start location, which is probably this one right here, is almost 43 miles, which isn't a realistic distance to make round trip twice a day. I'm going to jump back over to our slides. There we go. All right, and so like I mentioned before, we focused on clusters 2 and 3, and so we're going to look at some more specific information about these and some findings that we made. Cluster 2 was on the higher end of child poverty levels for our clusters with an average of 27%, and it also had an average number of 14 Head Start funded slots per tract, which, considering the average population is around 4,000 people, is not very much. It also had the second highest percentages of both Hispanic and white populations at 42 and 44% respectively, and was on the higher end of the average income as well. So a conclusion that we came to based off of this information, and that in New Mexico, the white population statistically has a higher average income, is that the white population may be bringing up the cluster's average income despite also having high levels of child poverty. For example, a neighborhood near where I live on one end has older, more affordable houses, and on the other end has bigger houses with nice views of the mountains and cost significantly more. The income of the people who live in that part of the neighborhood is raising the average for the whole neighborhood. In this case, the whole neighborhood could have a lower priority or even be disqualified from access to these services. And so for cluster 3, this one had a high average level of child poverty at 38%, and it also has a low number of funded slots and a low average income. This cluster also had the highest average of Hispanic population with 74%. Based on this and our info from cluster 2, we have concluded that the Hispanic population was the most underserved population.
Using a ranking system, we use the child poverty rates, income per capita, and distance from Head Start centers to design a ranking metric that identifies the most underserved communities. By using the mean values and standard deviation from these three categories, we created a standardized scoring system allowing us to rank communities by their level of need. Using our ranking system, we determined the top 5 communities in need of investment. You can see that the child poverty rates are more than double the national average for youth in neighborhoods of Otero, Doña Ana, and Bernalillo counties represented here. The income per capita in these neighborhoods ranges from 8,000 to 13,000. Looking at the racial ethnic data, communities of color are generally underserved by Head Start, and Hispanic communities are disproportionately underserved. Although we chose the top 5 communities based on child poverty, income per capita, and distance from Head Start, there are over 100 communities we found are underserved.
In conclusion, XGBoost and hierarchical clustering gave the best results overall for our data set and problem definition. With these models, we've identified that the Hispanic community is the most underserved by Head Start in New Mexico. We have identified the census tracts that can benefit the most from additional funding and could potentially make a noticeable difference in the lives of children that live in these areas by reaching out to those communities and encouraging them to apply for funding.
All right, so we also identified some next steps for moving forward. Step 1, many of the tribal Head Starts and early Head Starts in our data collection process were dropped due to incomplete information. And considering disproportionately higher rates of child poverty among Native populations, it's important to continue researching center data to ensure equitable access to preschool. Step 2, the 2020 census is wrapping up, and we hope to include updated social and economic characteristic data to inform our model and improve accuracy of identifying communities that are currently underserved. It would also be interesting to see if there are any significant changes, as most of our data is from around 2017 to 2018. Step 3, we'd like to update our map to include even more information and make it more applicable to someone who is looking to gauge the likelihood of their neighborhood qualifying for a Head Start center. And lastly, step 4, using our map to identify underserved communities, we can begin to engage Office of Head Start officials on guidelines for applying to program grants and launch a data-driven community engagement strategy to connect with neighborhood leaders and local advocates to increase access to preschool through Head Start. So thank you for taking the time to attend our presentation today. We appreciate all of you here. We'd like to open up for questions now.